Okay, so big O notation is very simply a mathematical concept. What it looks at is an algorithm. It looks at within the algorithm how efficient it is, efficient against runtime or space requirements. So how long it takes to execute the algorithm or how much memory it takes based upon the algorithm itself. So for example, if I was to put in this code, let me just zoom in to this code. Okay, let me just make this a bit wider. Alright, so we've got a function here. This function in itself will take in an array. It's then going to loop through every item in the array and put it into this array called copy. Now, what's going to happen is the amount of memory we can have. Let's imagine we've got 1,000 items in this array. When this function runs, it's going to then take up more space in our RAM because we're having to duplicate this 1,000 and put it into this array of 1,000. So it's not very efficient if we're talking about space. So we're now going to have a look at some different variations you need to be aware of when it comes to big O notation. Where the first one is going to be O bracket 1. What does this mean? Well, O stands for order of, which is basically used in mathematics and computer science, and it's going to describe our growth rate. The 1 is representing a constant time. So let me explain. Let's imagine right now that we've got a bookshelf. In our bookshelf, we've got 1,000,000 books. So starting on 1, finishing at 1,000,000. But I say we're always going to get the first book. So you're going to go in, get the first book. It doesn't matter how many books you've got in your bookshelf, we're always going to get the first book. We're instantly going to grab the book on top. So this is an example of a constant time operation. It doesn't matter how big our array is. The time it takes for us to perform this algorithm is going to be the same. So for example, let's put this into action. We've got our function, which is get top book. It's going to get our, let's imagine this was 1,000,000 books. We pass it into this function, and we're always going to just get the first book, which is Harry Potter. It doesn't matter how big our array is, the time it's going to take is going to be the same. So it's not reliant upon the size of the array. So we call that a constant because the order of growth is fixed. This is fixed. And that's an example I've just shown you there. Let's put it back in. Of an algorithm which is just going to be fixed, a constant. So O1. So we're now going to be looking at ON, which we call linear time. So let's go back to the book situation. We do have now, let's say 1,000 books. And the idea is that we want to search for the Bible. This function is going to perform a basic linear search. It basically is going to go through each one at a time until it finds it. The worst case scenario is that it has to go through all 1,000. The best case scenario is we find it in one go. But we have to look at the worst case scenario. So therefore, this is ON, linear time. It's less efficient than O1. So the N is basically representing a variable in itself. This means that the input data doubles in size, time or space, then the algorithm doubles. We're relying upon the amount of data we've got in our list this time. So the relationship is proportional to the input size. Because we're having to go through each one. It's different to when we had it as a one where we just access this, or let's imagine that we just had this print books 1. we go direct to here. That would be O1. This is where we have to go through each one, and we're relying on how many we've actually got in the list in the first place. So that is ON, linear time. So we've looked at O1, which is very simple to get your head around, and now ON. Let me just add constant. So what happens next? So we've had O1, which is constant, we've had ON, which is linear. Now we've got to have ON squared, which is quadratic. I can't spell quadratic. Nope. Quadratic. There you go. Okay. The rule for this is simple. We've got nested for loops here. These for loops are looping through the same data. So it literally, we're saying that the execution time of an algorithm increases quadratically as the size of input increases. So this basically means if our input size doubles, the execution time increases by 4 because of the very fact that we're looping through it twice. So if we double it, it's going to be 4. It doesn't matter in this situation that we've got I plus 1 in this, which is going to, you could argue, reduce the amount of searching we're going to have to do. So this code is simply going to match students against other students to look at their grades. That's what it's looking at. It's a comparison. It doesn't matter that this is going to run slightly less. It's still going to be quadratic in its very nature of having inner loop and outer loop. So for example, student A, we're going to compare their grade against student B. It's not going to let us, based on this code, then compare B against A because of this. Now, it doesn't matter, it's still going to be quadratic because we're recognizing that for each element in student in the list, we're performing a linear operation in the inner loop. So it is impractical over if our input size is huge. So the larger our input, the more impractical it gets. So where else, or what other algorithms have we used where we have like a nested for loops? So you could say like a bubble sort is a great example of this. So the final thing we're going to be looking at is O log n. So this is looking at a concept called logarithmic time. So I want you to imagine you're searching for a word in a dictionary. Instead of going through each word one by one, what we're going to do is we're going to open it up to the middle. So we go to the middle of the dictionary and we decide the word we're looking for is before or after that point. So let's imagine we're looking for apple. That's the word we're looking for. And the middle of the dictionary is hotel. We know that apple is going to be before hotel. So what we're going to do is we're then going to go to the middle point of the left. So you go to the left, find the middle point, and let's imagine we're going to be at donkey. We then need to decide, is apple before donkey or after donkey? And we know it's before, so we then find a middle point between apple and donkey, which is, or A and D, which is going to be, let's say B, let's say Britain. And then we know it's going to be to the left of that, etc. So what we're doing is, each step cuts our search area in half. So the time it takes to grow logarithmically with the number of words or pages. So what do we mean? Well, O log n represents an algorithm. It's an algorithm whose time complexity grows logarithmically as the size of our input data increases. So the bigger we've got with our input data, the complexity will grow. The number of operations will grow. The amount of times we need to put something in half and then half again, and half again will grow. So what is logarithmic? Well, the concept of it is easy to understand if we use this binary search. We know that in a binary search, instead of looking at each element sequentially, what we tend to do is we go to the middle, and then we go to the left, or we go to the right of it. So after one comparison, we know that the target is either left or the right. The next step is we repeat the process, we cut it down in half, we change mid again. And we keep doing that. So if a list has 16 items, the maximum we're going to do in terms of steps, it's going to be 4 steps to find our target, if it's in or not in our list. That's because 16 equals this. For a list of 32 items, it's going to take how many steps if it's 32? 5 steps in order for us to actually find it. So log n is efficient at scale. Doubling the size of input data only requires one additional step. So if we go from 16 to 32 items in our list, it's only going to take us now 5 steps to find that item. Where if it's sequential, it's going to have to take 32 steps potentially. So basically it's far more efficient than if we were going to be doing any type of sequential algorithms, or linear algorithms, should I say. This is a quick overview table of the different things you need to know for big O notation. Just keep in mind where I've got a red X, it is that I've never seen a question in regards to those. Feel free to do your own little research into wherever the X is. So if we're comparing algorithms, let's take the linear search versus a binary search. What do we know about, first of all, any requirements? Well, linear search does not need to be in order to start off with. Binary search has to be in order. So if we're doing a comparison, that'll be the first thing we would check. Is our list in order? Yes, it is in order. Or, no, it's not in order. That'll be the first thing we're going to look at. Then we're going to be looking at time complexity of both linear and binary. So let's do linear search to start off with. So the best case situation is O1, that we find it straight away. It's in the first position, whatever we're looking for. The average case is going to be ON, and the worst case, so ON obviously would be whatever we're searching for is in a random position. ON, it would be in the last position or not in our list at all. In terms of time complexity for binary search, best case, we find it straight away. So O1. Average case, it'll be O log n. So remember, it'll be like doubling, just increases the steps by 1. And worst case, the same, O log n. So from a time perspective, binary search is better than linear search. What about space complexity? Well, it's literally going to be O1. We're not going to have any additional space required for this. It's a constant. So the amount of RAM we're going to be using is going to be fixed. We put our array into the RAM, so to speak, and we search through it until we find the item. It doesn't grow. The same for a binary search. It's going to be O1 if we're going to be using iteration. If we decide to use recursion, it's going to be less efficient when it comes to memory space. So it's going to be O log n. And that's because when we do recursion, not only are we going to have space for the array, we're also going to have to space for our stack to wind and unwind. So that's going to take up more memory, and that depends upon the log n, how many steps we need. So if we were going to go for a fixed, or should we say an in order list, time is better for binary search. And if we're going to use iteration, just use loops to search for it, perfect. If we're obsessed with doing recursion, it's going to be less efficient when it comes to space than a linear search. Keep that in mind. And finally, for ADT operations like linked lists, binary tree, stack, queues, we can actually look at big O notation for the different aspects. Pause the video and have a read of it yourself. So if we take into account stack, because we're adding items always to the top, it's going to be O1. If we pop, it's always going to be O1. If we're searching, we're going to perform probably a linear search, so it's going to be ON to find the item, and same with a queue. It's going to be different for when we do binary tree, because with a binary tree what we're doing is when we're searching is that we're checking the different pointers, and we're going through the pointers in that order, so we're going to be using log n and normal case. Or we could use, if we're doing a linear search, ON. These are just examples. Linked list, if we delete something and it's at the head, it's O1. If we delete something at the end or in the middle or finding something to delete, it'll be ON. Same for inserting. If it's at the head, at the beginning, it's O1. If you need to find where we're going to put it in a certain point, it's ON. And searching may require us to go through the whole linked list.